In this video, we're going to take a look at solving equations with rational exponents. And when we talk about rational numbers, we talk about ones that are not irrational, such as pi or any decimal that would go forever without repeating. Okay, so we have whole numbers are rational, integers are rational, positive and negative whole numbers, decimals, because they could be written as a fraction, and any fraction is obviously already written as a fraction. So by definition, a rational number is any number that can be written as a fraction. Okay, so for us to be able to move into problems such as this, we need to be aware of something that I'm going to call the reciprocal exponent property. Okay, and we're going to take a look at it just here on this expression where it says x raised to the power of a over b. A over b being a rational exponent because obviously it's written as a fraction. Therefore, it is rational. Okay, well, this being the case, I want you to imagine for a second that somebody said we're going to take this expression and raise it to the b over a. Now, if you notice, this would bring into play the idea of the power-to-power property. The power-to-power property says you're supposed to take exponents and multiply them. Okay? Well, if I were to do that, the product of any two reciprocals is just 1, so I would be getting x to the first and not need to write the 1. So we see here that something really interesting happens. We see that if we have a base raised to an exponent and then raise that to its reciprocal, it kind of cancels that exponent, which is great because when we solve equations, we look to work backwards and do these cancel things that we've learned. We've tended to use the additive inverse properties to cancel and the multiplicative inverse properties to cancel. And now we've got an inverse property here for exponents, it seems, which is just raising an expression to the reciprocal. So just to sort of elaborate that a little further into these three examples, I'm going to try and apply the reciprocal exponent property just sort of randomly so you kind of see how it works. These are not equations, you're not solving them, so you have to kind of just have to suppose a little bit that if you were given m to the 2/3 and then raise that to 3/2, the 2/3 and 3/2 would cancel each other when you do the power-to-power property, and you would in fact get m to the first. And then similarly, if you had b to the negative 1/6 and decided to just say, well, what would happen to that expression if I raised it to its reciprocal exponent? Well, the reciprocal of negative 1/6 is in fact negative 6. It's not 6. Remember, when you do the reciprocal of a number, its sign does not change. Some people confuse this with the notions of perpendicular lines learned long ago where they heard the word opposite reciprocal. Well, opposite reciprocal is particular to that type of problem, but not here. So, getting back to this, if I had b to the negative 1/6 all raised to the negative 6, the product of those exponents again will be 1, leaving me with just b to the first written as b. And y to the 12th, here we do have a rational exponent, because don't forget it is 12 over 1. All whole numbers are rationals and they could be written as fractions. And if I were to suppose raise this expression to its reciprocal exponent, those exponents would cancel each other by the power-to-power principle. I would get y to the first, which would just be y. So how does this look as we move into solving equations? Well, let's take a look here, okay? And I'm going to try and follow these general steps. They're more of guidelines, okay? But it's a good algorithm to sort of have in your back pocket to when you approach these problems. The steps say, 1, isolate the base with the exponent. Now keep in mind the base might be a monomial or a binomial here. That's why I don't say the variable, but I say isolate the base with the exponent. 2, apply the reciprocal exponent property. And now, because in the following problems we're going to do their equations, you do have to do it on both sides. Back here, I was just sort of toying around, sort of a sandbox type approach to play around with these to show you what happens when you use reciprocals. But when I move forward to using equations, remember, golden rule of algebra says whatever you do on one side of an equation, if it changes the expression, you must do it on the other side as well. And then step 3, continue to solve for the variable if needed. Okay, so you might, in just doing step 2, when you apply the reciprocal exponent property, it might in fact get the variable by itself. So let's take a look and see how this goes. The directions say here, please solve the following equations. Round the answers to the nearest 10,000th when necessary, which is 4 decimal places. Okay. And I will take a look at this by way of the steps. In the first problem, it says 2x to the 5/12 plus 7 equals 12. So it says here that step 1, isolate the base with the exponent. The base with the exponent is just simply x in this case. So I'm going to try and get the x to the 5/12 by itself. This should not come as a surprise that I'm going to subtract 7. Get 2x to the 5/12 is equal to 5. And then I'm actually going to divide both sides by 2. And that will give me x to the 5/12 is equal to 2.5. It's an okay time for a decimal here because it's finite. It's terminating decimal. And now that I've done that, I'm here looking and saying I've gotten the base with the exponent by itself. And now I'm going to apply the reciprocal exponent property. So I'm in fact going to raise both sides here to the reciprocal of 5/12, which is 12/5. And extend my page just for a second. That is in fact going to give me x equals. And we see just by the property it's x to the first because the reciprocals will cancel each other and create an exponent of 1 when I do the power to power principle. And then just through the assist of my calculator, it makes sense to do 2.5 to the power of 12/5, which on my calculator I'll make sure I group in a set of parentheses, which is important. And that is going to give me 9.0169 when I raise it to 4, when I round it to 4 decimal places. 9.0169. Okay? And as that is in fact a solved problem, okay, I'm going to use the store button on my calculator and do 9.0169 store x. Okay, there's a reason I did not hit answer store x. Okay, what I'm doing here, if you can anticipate, I'm actually checking it. It's a solved problem. If this is x, it should work when I plug it in. So I want to show you that when I do 2x to the 5/12 plus 7, I'm anticipating that I should get 12. Well, if you notice, I don't exactly get 12. But the only reason I don't get exactly 12 is because my answer was rounded, probably making it a little bit more appropriate to say x is about. Okay? 9.0169. This answer seems pretty legit to me. It seems to create a result of 12 almost when I plugged in, taking into account the rounding. So I'll move over to my next problem here. If you notice, it's a little different. It looks like it's a binomial. Okay? And some kids see a problem like this and say, oh, I need to raise this to the 1/4 somehow. Well, you're not going to do that because don't forget we're solving. We're working backwards. Okay? So don't be frightened by that and say, oh, this problem's different because it's a binomial raised to the 1/4, so I need to figure out how to do that. Well, you're not going to do that. You're going to undo that. So let's take a look back up here a little higher at my steps, okay, where it says isolate the base with the exponent. In this case, I hope you realize that the base with the exponent here is this binomial. So a little different approach here, but same kind of general guidelines in this algorithm here. Okay, so what am I going to do? The first thing I want to do is realize that this is in fact a -1 out here, or could be seen that way. So I'm going to divide both sides by -1 and get the quantity of x minus 5 to the 1/4 is equal to 9. Now that I have in fact isolated the base with the exponent, I'm going to raise both sides to the reciprocal of that exponent. Okay, so what does that look like? When I deal with the reciprocal of 1/4, it is going to be 4. So I will raise both sides to the 4th power. My writing here, I group the entire side here and raise it to the 4th. And then I have 9 to the 4th on the right side. Well, again, 1/4 times 4 will create an exponent of 1, which is what's so neat and tidy about doing this, which means on the next line I would just have x minus 5 equals 9 to the 4th, which is going to be, in fact, 6,561. And then in step 3, it says to continue to solve for the variable as needed. You probably realize why I put that step in, because these are problems where you have binomials. We've not really gotten the variable completely by itself. So I will add 5 and get x equals 6566 as a result of adding 5 again on both sides. And I will check that answer, 6566, store x. There's nothing to round here, so I would expect this to be an exact match here when I check it. So we've got the opposite of the quantity of x minus 5 raised to the 1/4 in a group, and I'm hoping that I get a result of -9, which I do, which makes me realize that this is in fact the correct answer. Okay, do one more example for you. Okay, it's one where we've got a binomial again. Good to show you more examples of that because they are in fact a little harder, a little awkward to write. So a little practice there will help you. So I'm going to isolate the base with the exponent. If you see here, the base with the exponent is in fact again this binomial, 2x plus 4. So I'm going to work on getting that by itself first, which is decently easy here. It looks to be if I just add 8 to both sides. Okay. 28 equals the quantity of 2x plus 4 to the -7/3. And again, don't fret if you don't know how to raise something to the -7/3 because you're actually not going to. You're going to undo that. Okay, so now that we've gotten that base by itself, we're going to raise both sides to the reciprocal of that base. Again, the reciprocal of -7/3 is -3/7. Again, the sign does not change when we take a reciprocal in these problems. So I'll do that on both sides. Okay, now there's a little twist here if you notice in a problem such as this. Okay, on the right side of the equation, you see that I'm going to get 2x plus 4 because these exponents will cancel when I do the power-to-power property. Okay? Now on the right side, on the left side, I kind of get this little bit of a mess for now. So I'm going to kind of give you a little stylistic thing about how to write this. 28 raised to the -3/7, which is kind of a mess, right? Well, it says to round to 4 places. It's good practice to try and round in the end of a problem to avoid what's called round-off error. Because if you round now and now need to round later, you're rounding twice and you might be rounding too much. Rounding is kind of an annoying practice a little bit sometimes, but it's definitely a skill we obviously must have. So the one thing I'm actually going to do for now is actually I'm just going to leave this as 28 to the -3/7. And then I'm going to continue with the problem by subtracting 4. Okay? And then doesn't that give me 28 to the -3/7 minus 4 is equal to 2x? And then from there, still avoiding that sort of ugly decimal on my calculator, I'm going to multiply both sides by the reciprocal of 2, which is in fact a half. Okay? So some people might think this is awkward. Some people might think it's elegant. This is going to give me 1/2 times the quantity, 28 to the -3/7 minus 4, which I think is then a good time to go to my calculator and do 1/2 times 28 to the -3/7 grouped in a set of parentheses for my calculator using this operating system, minus 4. Okay? So that is going to give me a result of negative 1.8801. Okay? And I'll check that answer. Now, let me do this here and show you that I'm not actually going to round this answer, but my answer is actually rounded on the board. So I would just hit store X to put that answer back. Okay? Now, I should get an exact match here because I've stored the exact value, although I didn't write the exact value. So I'm just going to kind of think as I'm doing this and go back to the original problem and say, is it 2x, quantity of 2x plus 4, excuse me, raised to the negative 7/3, right? Minus 8 hopefully will give me a result of 20, which is great because I would hate to have to start this video from the beginning to get it all correct. So I feel good about this answer as well, okay? And I feel even better about this algorithm that I used, which is, again, some general guidelines that say isolate the base with the exponent, apply the reciprocal exponent property, which I'll review again in a second, and continue to solve for the variable if needed. I hope this modeled also about using your calculator appropriately. So again, the reciprocal exponent property just simply states if you have a base raised to an exponent, if you raise it again to its reciprocal, it nullifies that exponent, which is a great handy thing in these problems where you are trying to, in fact, work backwards. So again, you can use your calculator to check and be mindful of your rounding and how that impacts your work as you do so. Enjoy. I hope this was helpful. Feel free to watch it again, and thanks for your time.